All right, good morning, everybody. This is Math 0310. It's March 29th. A couple of announcements to make here to get started. Web assigned homework, all the Chapter 10 homework, and that's, I believe, is like 4 sections, 10.1, 10.2, 10.3, 10.4. Those 4 sections are due April the 3rd. I've kind of postponed that a little bit. So you have through the Easter weekend coming up, and then you have also Monday and Tuesday of next week as well to get those turned in or get those finished. So don't get behind on the web assigned homework. And let me know over the weekend. I will be checking email over the weekend. So don't hesitate to email me or send me a remind message or web assign message if you have some questions. Exam 2, I'm still in the process of getting some of those tests. But I will be working on those over the next few days, and I'm hoping to have your grades posted by April the 2nd at the latest. Right now I'm going to say April the 2nd, and hopefully earlier than that. So I should make some pretty good progress on your test today. I will send a remind message when I have posted your grades. All right, so be looking for that. I'll post your grades on your web assigned gradebook. And then don't forget that you can always email me, and I will send you a copy of your graded exam back. W Day is April the 6th. That's actually a week from tomorrow. And so remember what W Day means. That is the day where if you are enrolled in a class after that day, then you cannot get a W in that class anymore. And so be thinking about that as far as my class goes. If you have any questions about your grade, I'm the one you should talk to. Talk to me, email me, and we can discuss what your grade situation is like in the class if you have some concerns. Online office hours, I haven't reminded you of that recently, but remember that I am available online, and we're kind of going through regular office hours right now. So my regular schedule is Tuesday, Wednesday, and Thursday from 11 to noon, and then Tuesday and Sunday evening from 8:30 to 9:30 p.m. So don't hesitate to come by my office if you have any questions, my online office, okay? And today, we are going to have a big shift in the class. We have been talking about solving quadratic equations out of Chapter 10. We've looked at all the methods for solving quadratic equations. And so now we are going back, and we are going to talk about graphing and looking at equations in 2 variables. And so that's a huge shift from what we've been talking about. And so that's what we're going to discuss today is some introductory material on graphing. All right, so when you're talking about graphing in the plane, you're necessarily making the shift to equations in 2 variables. Right. And this is not something we have talked about so far this semester. We're talking about equations in 2 variables. Typically x and y, but it doesn't have to be x and y. And so if you have an equation in this form, 2x plus y is equal to 6. 2x plus y equals 6. We see that's an equation in 2 variables. Right? It's got an x and a y. And solutions to equations like this, I'm assuming you've done some basics with this, but I'm going to kind of go back over those things again as we go through this. Solutions are ordered pairs. And remember, an ordered pair is a number that looks like this. It's a pair of numbers we write inside parentheses where the x coordinate is first and the y coordinate is second. And the solutions are ordered pairs so that when you substitute them in, you get a true statement. Right, so for example, the ordered pair 1, 4 is a solution to this equation. And why is it a solution? Because when you put 1 in for x and 4 in for y, right, you get a true statement. You get 6 equals 6, you get that that's true. Right, so 1, 4 is a solution to that equation. On the other hand, negative 1, let's say negative 1, 7 is not a solution. Right? Because when you substitute -1 in for x and 7 in for y, you get 5 on the left side equals 6. And so that's a false statement. Right? And so -1/7 is not a solution to this equation. Now, what makes this really different when you're talking about equations in two variables like this is, okay, so you've got this solution 1,4 that I wrote down for that equation. But, for example, the solution or the ordered pair 0,6 is also a solution, right? Because when you put 0 in for x and 6 in for y, right, you get a true statement. So that's 0,6 is a solution. The ordered pair 1/2, 5 is a solution. 2 times 1/2 plus 5 equals 6. And so you get 1 plus 5 equals 6, which is true. -5, 16 is a solution because you get 2 times -5 plus 16 equals 6. You get -10 plus 16 equals 6. That's true. What happens here and why this is really different from equations in one variable is that I could go on with this list forever, right? This list of solutions is infinite, and equations in two variables typically have solution sets that are infinite. They have an infinite number of ordered pairs that are in those solution sets. And see, so you can't just list the solutions to the equation like we could equations in one variable, right? So if you had a typical, let's say, a quadratic equation in one variable, right, that might be something like x squared minus 2x minus 3 equals 0. That's a quadratic equation, and notice it has just one variable in it, just x's. And we know how to solve this, right? X minus 3 times x plus 1 equals 0. You set each factor equal to 0, and you get x equals 3 and x equals -1. So what can you do here? You can actually list the solutions, and that's what we do. We list them out in a set. There's two solutions to that equation. It's -1 and 3, and we actually write a little list as the solution set for this equation. All right, so equations in one variable are typically like this in that they have the number of solutions that they have is finite, and so you can actually list them out. But equations in two variables are really different because there's too many solutions typically to list because the solution set is typically infinite in length. And so because the solution set is infinite, has an infinite number of ordered pairs in it, so most solution sets for equations in two variables are infinite in length. So instead of listing the solutions like we do equations in one variable, so instead of listing the solutions, we draw a picture of the solution set. In the coordinate plane. And that little phrase right there, where we draw a picture of the solution set in the coordinate plane, that's what I'm highlighting right here. That's what we are referring to when we say these words. When we say graphing an equation, that's what we're doing, is we are drawing a picture of all the solution sets in the coordinate plane, or of all the solutions in the coordinate plane. And so we usually don't say we're drawing a picture of the solution set in the coordinate plane. What do we usually say? We just say we're graphing this equation. But that's what we mean when we're graphing an equation. All right, so that's what we're talking about doing, okay? And so that's what we're all about in this problem. Now, if we take, now remember the coordinate plane, well, let's take the equation that we were looking at on the last screen, 2x plus y equals 6. You know, we wrote down a number of ordered pairs that were solutions to this one. So we wrote down 1, 4 was a solution. We wrote down 1/2, 5 is a solution. We wrote down 0, 6 is a solution. 3, 0 is a solution, right? We could, like I said, we could continue on with this list for quite a while. 4, -2 is a solution, right? All of these ordered pairs are solutions to this equation. 5, -4 is a solution, right? Remember, this list is infinite. So to graph this, we go to the coordinate plane. So the coordinate plane, let's remind you of several things that are going on here. Remember, in the coordinate plane, we have two axes. We have the horizontal axis, which is the x-axis, and the vertical axis, which is the y-axis. This point at 0, 0, right? This is 0, 0 right here. That's called the origin. And don't forget that the x and y axis divide the plane up into 4 sections, and those are called quadrants. And so this is quadrant 1, and we number these counterclockwise, usually with Roman numerals. So this is quadrant 2, quadrant 3, and quadrant 4. So we'll refer to the quadrants relatively often when we're talking about graphing. And so then we just locate these points in the plane. You know, we use the x-axis and the x-coordinate, the y-axis and the y-coordinate. And so we plot these points. So you get 1, 4 is this ordered pair right here. All right, 1/2, 5 is this ordered pair right about in here. The x value is 1/2, the y value is 5. 0, 6 is this point. 3, 0 is this point. And never a bad idea to label these, by the way. So there's 3, 0. This is 1, 4 right here. This point is 1/2, 5. This point is 0, 6. Never a bad idea to label the points, because if you're sketching a graph that you want me to see, you know, if you're not entirely accurate, but you have it labeled correctly at least, you know, you probably have a better chance of getting that correct. So here's 4, -2, and 5, -4. Right, these are the solutions that I've calculated so far for this particular line. All right, so notice that all of these points are line on a line, and that's the graph of this solution of the solution set to this equation is this line right here, because every solution to this equation lies on this line. And so we say that that line is the graph of the solution set for that particular equation. 2x plus y equals 6 is what we call a linear equation in 2 variables. So it's a linear equation in 2 variables. And it's a linear equation because it's a first degree equation, right? The x and the y are both raised to the first power. All the terms are first degree terms. And as it turns out, any equation that's a linear equation in 2 variables, this is a good thing to know. So this is the general form, ax plus by equals c. So this is the general linear equation in 2 variables. The graph is always a line. Right, so the graphs are always lines. Right, and so that's very good for you to know as an algebra student, that when you encounter a linear equation in 2 variables, the first thing you say to yourself right away is, hey, I know that this graph's a line. Right, that's a very important thing to know right away, is be able to recognize a linear equation when you see one, and equations also that are not linear. Right, and we'll look at that in a second. All right, so some other features of this graph that we want to talk about here. In particular, let's see. In particular, this point at 0, 6 that I'm highlighting in 3, 0, those points are called the intercepts for this graph. And so the x-intercept is this point 3, 0. It's where the graph crosses the x-axis. And the y-intercept is the point 0, 6. Right, it's where the graph crosses the y-axis. And those are what we call the intercepts. All right. And because if we know that the graph's aligned, think about it, the intercepts are really the only points that really ultimately end up being necessary for graphing the line. So, because all you really need are 2 points to be able to graph the line. All right, so some of this hopefully is definitely a review for you, and you've seen it before in another class. For example, if you've had introductory algebra in the Lone Star system, you should have talked about lines in graphing lines in introductory algebra. We're just going to go in a lot more detail in this class because we're setting you up for college algebra. And in college algebra, we are sketching graphs just absolutely constantly. So if you look back, this, by the way, would be helpful for you to look at. If I show you the notes from my college algebra class from yesterday, what I want to point out to you is that notice that on most of these pages, there are graphs, right? We're looking at particular kinds of graphs. This is just from yesterday's class. So almost every page, notice every page so far I've been through has got graphs on it. Now, there's a few things here at the end where are applications, but most of this has graphs on it. And so virtually every page yesterday had graphs. We had t-tables, lots of different things that we were looking at with graphing. And so if you go back and look at any of my notes from college algebra, any notes from college algebra, you are going to find that, let's see, so these are all my notes from college algebra. And so I'm kind of going through here and picking out just almost a random, and watch me have picked one where there's not a lot of graphing. And this one, there's not quite as much probably, but some, definitely, right? You have a graph on that page, graphs on that page, nothing on that page, graphs again, and so lots of things having to do with graphs in college algebra. Almost any particular day, you're going to run into graphing in college algebra, okay? So it's really important in this class that we set this up correctly so that when you walk into college algebra, you're pretty comfortable with sketching basic graphs and some basic things about lines in particular, all right? All right, so now let's talk a little bit about linear equations here. So let's say we have y equals 5x plus 8. Now, it's not in that form ax plus by equals c, but each term is a first-degree term or a constant. When I say a first-degree term, remember the x's and the y's are raised to the first power. So this equation is a linear equation in 2 variables. All right? Y equals the square root of x plus 6. This one is not linear because you've got an x underneath the square root, and so it's not a linear equation. Y equals 1 over x minus 3. Not linear. Right? So when we say it's not linear, we're saying that these equations, graphs are not lines, right? These graphs are something else. And we're going to talk about some of these basic graphs later in a few days in class about plotting points and things like that. Y equals x squared minus 3x plus 8. Not linear. This is a second-degree equation, right? So this is second degree, and so its graph is definitely not a line. Let's see. Let's say we have 8 minus 3x equals 2y plus 7. 8 minus 3x equals 2y plus 7, even though it's kind of a funny form. All the terms are first-degree terms, and so this is a linear equation right here, right? These, because the x's and the y's are all raised to the first power, they're all first-degree terms. So you want to be able to recognize linear equations when you see one. By the way, x equals 8. Even though there is no y in that equation, it doesn't matter. This is still considered a linear equation in two variables. Technically, this is x plus 0y equals 8, that the coefficient of the y is a 0. So that x equals 8 is a linear equation just like the other ones on this screen and on the previous page. Same thing with y. Let's say we have y minus 6 equals 0. Notice there's no x in that one. That doesn't matter. It's still linear. Technically, that would be 0x plus y minus 6 equals 0, right? So, 0y is really the same thing as 0, and 0x is really the same thing as 0. And so you can think of those as linear equations in two variables, even though the second variable is not in the equation, right? So these are the kinds of equations we want to talk about graphing. All right, so generating ordered pairs that are solutions to these kinds of equations. So let's just graph by plotting points. That's what we're talking about, and t-tables. So graphing lines by plotting points. And when we're talking about plotting points, we are talking about something called t-tables. All right, so let's see. Clean that up just a little tiny bit here. So we're talking about t-tables. So if we have the equation y equals, let's say, negative 3x plus 1, right? We can graph this line. We can generate points on this line by creating a t-table. And this is just like a little table, and sometimes you'll see it written vertically like I'm doing here. Sometimes you'll see it written horizontally. And because the equations solve for y, this is very convenient to just pick x values. And the nice thing is you can pick any x value you want. So I could pick a nice little representative sample of x values. Like I might pick negative 2, negative 1, 0, 1, and 2 as a possible set. I could pick any x values I wanted to here. But if you think about it, you want to make this as convenient as possible. So you want something that makes sense as far as you're about to draw a graph, and so you don't want values that are too big. And all you're doing here is you're simply saying that y would be equal to negative 3 times negative 2 plus 1. Right? You're just substituting negative 2 in place of x. And so you get that y is 7 right there. When x is negative 1, you get y equals negative 3 times negative 1 plus 1, which is 3 plus 1, or 4. When x is 0, you get y equals negative 3 times 0 plus 1, which is 1. Put in 1, you get negative 3 times 1 plus 1, which is negative 2. Notice, by the way, that there seems to be a pattern here in that as the x value gets bigger by 1, notice in this particular problem, the y value is getting smaller by 3. Every time it decreased by 3 units. Not a coincidence. That's definitely true for this line, and this is definitely a kind of pattern that you'll see with every linear equation in two variables, that this is always going to be the kind of thing that's going to happen. There's going to be a pattern to the y values. That's a characteristic of all linear equations. Put in 2 for x, and you get negative 5. Negative 6 plus 1 is negative 5. All right, so that gives you a nice little representative sample of, and I don't know if I can get necessarily all of these in here, but I'll get as many of these on here as I can. All right, so you have negative 2, 7. So negative 2, and then 7, 1, 2, 3, 4, 5, 6, 7. It's way up here where I was writing down problems. So there's negative 2, 7, and then negative 1, 4. 1, 2, 3, 4 is here. 0, 1. Because you know this is a linear equation, you know that these points better lie in a line. And if they don't lie in a line, you know you've done something wrong. Here's 1, negative 2. Notice this is 0, 1, and remember that that is what we call the y-intercept right there. Notice that the y-intercept is always got an x value of 0. That's where the line crosses the y-axis, and the x value is going to be 0. And then the last point we have is 2, -5. 1, 2, 3, 4. Way down here. Right, and we definitely have all these lines, or all these points are lying on the same line. So we can get a nice sketch of this graph. Notice that the x-intercept for this graph, there is an x-intercept for this graph. We don't have it plotted. The x-intercept is some value between 0 and 1 right here. Right, that's the point right there. And what do we know about that point for sure is we know that its y value has got to be 0. In fact, that's how you can actually find the x-intercept, is you can actually set y equal to 0 in the equation that you've got. So that would be 0 equals -3x plus 1, or 3x equals 1, or x is equal to 1/3. And so notice you can actually find the x-intercept, and that makes sense in my graph, right, that it's going to be at the point 1/3, 0. That definitely seems to fit the graph right there, that it's crossing at about x equals 1/3. So you can always find these intercepts by substituting 0 in for x and 0 in for y like this, right? For the x-intercept, the y value is 0, and for the y-intercept, the x value is 0. We'll talk more about that in a minute. All right, so this one looks good. Let's look at another equation. The numbers don't necessarily always turn out quite so nice if you're going to plot points. So let's say we have 5x minus 6y equals 10. 5x minus 6y equals 10. All right, so if we wanted to plot points here, we could do that. We can make our little table of values. Everybody's okay? Okay, no questions? Just making sure. Again, it doesn't matter what x values you pick, remember? So you could pick, if you're going to plot points, you could pick our nice little sample of -2, -1, 0, 1, and 2, like this. So you have 5x minus 6y equals 10. And I'm going to do the arithmetic off to the side. When x is -2, let's do this over here. So x is equal to -2. You have 5 times -2 minus 6y equals 10. So you get -10 minus 6y equals 10. You add 10, you get -6y equals 20. And so y would be -20 over 6, or -10 thirds. And if you're going to graph this, you might want to write that as a mixed number, as -3 1/3. Remember, 3 goes into 10 3 times with one left over, so -3 1/3. So graphing -3 1/3 is actually probably somewhat better than -10 thirds, because it allows you an easier opportunity to find that value. So this is -3 1/3 right here. Now notice the arithmetic was kind of just a little bit ugly as we were going through this. We can make our lives a little bit easier on an equation like this if we make this equation look like the last one. So if you look at the last one, notice that this last equation, this was solved for y right here at the beginning. In other words, the y value is by itself. And so this equation was what we call solve for y. It was y equals. And when you're plotting points, having the equation in the form y equals is always nice, because it makes the arithmetic easier in general to create a bunch of points. So if you wanted to do that here on this problem, you could make your life maybe a little bit easier for the rest of these points by taking this equation and solving it for y. So if we solve for y right here, let's see, so solve for y, we mean getting the y value by itself. So we subtract 5x, and I'm going to put the 5x first, and there's reasons why I'm doing that will become apparent to you on Tuesday's lecture next week. So I subtracted 5x, and then I divided by -6. Now I know I'm going to get fractions here, but there's just no way to avoid that. So you have -5x over -6 plus 10 over -6, right? You divide term by term here is the easiest way to do this. And so this gives you y equals 5/6 x minus 10/6. And I'm actually going to leave the 10/6 like it is because they have the same denominator. It's just going to make my arithmetic easier. So with that equation in mind, then let's go ahead and pick the other x values. So here's where we picked x equals -2. So let's pick x equals -1. That's our next x value. See, so now look at the arithmetic. It's 5/6 times -1 minus 10/6. That's actually a lot easier to go through because this is just -5/6 minus 10/6 or -15/6. And that reduces to -5/2 or -2.5. So you get -5/2 right here or -2.5 is your next point. That's -15/6. All right, the next point was when x is 0. This one's going to be much easier to go through because your x equals 0 always makes the arithmetic nice. So you have 5/6 times 0 minus 10/6. That's just 0 at the beginning, so that just gives you -10/6. So you get which reduces to -5/3. So this is -5/3, which is -1 2/3. Use x equals 1. When I pick x equals 1, I get y equals what? 5/6 times 1 minus 10/6. And so that gives you 5/6 minus 10/6, which is -5/6. All right, so this is -5/6 right here. And then finally, when x is 2, you get y equals 5/6 times 2 minus 10/6. So notice that gives you 10/6 minus 10/6, which is 0. And so for the y value, you get 0 there. So 2, 0, kind of straighten that up a little bit. This, notice, because the y value is 0, remember that is the x-intercept for this graph. That's the x-intercept. All right, so if we wanted to sketch the graph, we now have definitely enough points to do that. To get a pretty good graph here. So let's see what this one looks like. You have -2, -3 1/3. So -2, and then 1, 2, 3, and you just estimate as best you can, especially when you have decimals, or I'm sorry, fractions like this. Really a good idea to label the points. And by the way, you can write -3 1/3, or you can write -10/3 there. Actually, most algebra students are going to write it as -10/3 right there. But actually thinking of it as -3 1/3 helps you graph it. And then -1 and -2.5 is right here. So that's -1 and -5/2. And then we get 0, -1 2/3. So right about here. That's our y-intercept. I didn't identify that before, but that's definitely the y-intercept for this graph because the x value is 0 there. And then you have 1 5/6. So 1 5/6 is not quite at -1. And then finally 2, 0, like so. And we get our line. Right? I tried to be as careful as I could about the points, and because I was using fractions here, and then once again, remember you've got these intercepts, right? So you've got the point 0, -5/3 is the y-intercept, and the point 2, 0 is the x-intercept, like that. So the intercepts are good to know for an equation like this. All right, let's see. Let's continue on with this. So the solving for y is not a bad thing to do. So if we have 3x plus 7y equals 0, if we're going to plot points, solving for y is not a bad thing to do. So if you solve for y, you get the y value by itself. So you subtract 3x, divide by 7, and you get negative 3/7 x. Y equals negative 3/7 x. And so that's the form we're going to use for plotting points. Right? And then we're going to make our little table of values here. Using our nice little representative sample, -2, -1, 0, 1, and 2 works just fine. The arithmetic is really pretty straightforward here because you have negative 3/7 times -2. That's just 6/7 for when x is -2. Y is 6/7. When x is -1, you have negative 3/7 times -1. You get 3/7. Notice that what's happening here is negative 3/7 times 0 is 0. Notice that the y value is getting smaller by 3/7 every time. Y equals negative 3/7 times 1, you get negative 3/7. And then finally, when x is 2, you get negative 3/7 times 2, or negative 6/7. Notice that the x and y intercepts on this equation happen to be the same point because the x value and the y value are both 0. So this graph actually passes through the origin. All right, and so let's see. So you've got negative 2 6/7, negative 2 6/7, not quite at 1. Negative 1 3/7, a little bit less than a half. 0 0. And then 1 negative 3/7 here, and then 2 negative 6/7 right about here. And so you get all these points are on a line. And that's the graph of our line. Notice that this line actually passes through the origin. And so that's both the x and the y intercept for this particular linear equation. All right, let's look at equations where the x or the y is missing. So like let's say we have x equals -2. So there the y is missing in this equation. Now notice you can't solve for y. So if I wrote solve for y here, you can't do it. And the reason why is because there is no y. The coefficient of the y is a 0. And so you really can't solve this equation for y at all, an equation like this. When you have x equals -2, an equation like this, the y value can be anything. Remember, because technically this means x plus 0 y equals -2. And so it doesn't matter what you put in for y. You're going to multiply by 0, and you're going to get 0. So what has to be true here essentially is that x must be -2, and I'm going to write that in words. X must be -2. Y can be literally anything. It doesn't matter because you're going to multiply by 0. So you have -2, 0. -2, 1, -2, 2, -2, -1, -2, -2, right? And so on. As long as the x value you've picked is -2, then you can write down anything for y, and that ordered pair will be a solution to this equation. All right, so when we go to graph this equation, in other words, plot these points, you've got -2, 0 is here. -2, 1, -2, 2, -2, -1, -2, -2. Notice that all of these points, they are all on a line, but this is a special kind of line that's parallel to the y-axis. And so this is our equation, x equals -2. And notice this is what we call a vertical line. And what ends up being true always is that if you have an equation that is x equals a constant, in other words, y is missing, the graph is always a vertical line. That is definitely something that you will want to know. That equations, I'm going to kind of put a box around that little statement here at the end, and I'm going to highlight it as well because that's important, that you recognize vertical lines that equations in the form x equals a constant, if the y is missing, that graph is going to be a vertical line. It's really nice to know that. As a college algebra student, you really need to know that. All right, so that's a nice little thing to always keep in mind. As a college algebra student, I can't tell you how good that would be when you walk into college algebra if you know that kind of situation, that kind of thing, and you know how to graph lines in general really pretty well. If you do, college algebra is just going to be so much easier because you're going to have some good basic graphing knowledge. Let's say we have the equation 2y plus, or let's say 2y minus 5 equals 0. 2y minus 5 equals 0. So notice in this example, the x is missing. And so what you do is you can solve for y in this equation, so do that. Add 5 and then divide by 2. You get y equals 5 halves. And now in words on this problem, what you can say for this kind of equation, you can say y must be equal 5 halves. X can be anything. Right? It doesn't matter what the x value is because the coefficient of the x is 0. And so you'll always get a 0 there. So you can put anything in for x here and it won't matter because that term will go away. And so if I make a little table of values over here to the side on this one, as long as y is 5 halves. So I could like pick my little representative sample here for x's, -2, -1, 0, 1, and 2. But y is always going to be 5 halves. It doesn't matter what you pick for x, because when I substitute in, I'd multiply that x by 0. So y must be 5 halves if this is going to be a solution. And remember, 5 halves is the same thing as 2.5. And so now I can graph the line. Whoops. There we go. So you get 0, 5 halves. You get 1 5 halves, 2 5 halves. Whoa, wait a minute. What am I doing? I don't know. I'm not paying attention. So you have, let me try that again. -2 5 halves is right here. That's so much better. -1 5 halves, 0 5 halves, 1 5 halves, 2 5 halves. Right? Those are the points right there. Oh, that's so much better. And so what do you get here? You get the graph to be a horizontal line. Here's y equals 5 halves is that graph right there. And so any equation in the form y equals a constant, in other words, the x is missing, the graph will always be a horizontal line. Right? So y equals, you always get a horizontal line. Definitely, again, a nice thing to know. Not just a nice thing to know, you really need to know that as you're going into college algebra. So you need to know what kind of graph you get when you have y equals a constant and what kind of graph you get when you have x equals a constant. Because that situation is going to come up frequently. And also, believe it or not, horizontal and vertical lines are pretty much the most important things for calculus students to be able to recognize. Is they're looking at horizontal and vertical lines all the time and with what they're doing with graphs, believe it or not. So those are very important lines to a calculus student. All right, so we've now talked about plotting points. Let's now move on to graphing by using intercepts. Okay, so graphing lines using intercepts. So this streamlines the process that we've just been talking about. So if you have 7x minus 3y equals, let's say, -5, you could graph this line using x and y intercepts. What I would do if I were you is I'd still make a little t-table if I was asked to find intercepts, but I would just modify how I'm creating the t-table. I would put 0 in for x on one point, and I put 0 in for y on another point. Right? When I put 0 in for x, I'm talking about the y-intercept. And when I put 0 in for y, I'm talking about the x-intercept. And that gives you a good little framework for what you're supposed to be doing with this equation. Right? You put 0 in for x and you solve for y. So you have negative 3y equals negative 5 and y equals 5/3. And so the y-intercept is going to be here at 0, 5/3. And then for the x-intercept, you put in 0 for y. So you have 7x minus 3 times y, 3 times 0 equals negative 5. That gives you 7x equals negative 5, or x is negative 5/7. And so x is negative 5/7 right there. And because the graph's a line, that is enough information to sketch the graph. You might not get quite as nice a graph as before, but as long as you're careful, you still get a graph of this line. So you have 0, 5/3, and remember 5/3, you get all sorts of crazy places where 5/3 is located, but that's 1 2/3. So you have 0, 1 2/3, right about here, let's say. And then negative 5/7, 0. Negative 5/7 is relatively close to negative 1, and the y value 0. And so those are my two intercepts, right? You have 0, 5/3 right there, and here you get negative 5/7, 0. And so that would be my line, is the line that passes through these two points like this. Right? And it's not quite as accurate because you don't have as many points, but it still gives you a decent sketch of the graph. Definitely a good thing to know. So, or be able to do is just intercepts give you a nice way of making quick graphs for lines. All right, so let's see. We're going to continue doing that. Let's graph using intercepts. Let's look at this equation. Let's say we have 2x minus 3y equals 0. So when you have an equation like this one and you're trying to use intercepts to graph, and a lot of you may see the writing on the wall right away on this, right? When I put in 0 for x or 0 for y, it doesn't really matter, does it? Because of the way the equation's written, I'm going to get 0 for the other variable automatically. You get y equals 0 here. When you put in 0 for y, because that constant was 0 on the other side of the equal sign, right, you're going to end up with 0 in both cases. And so what happens here, you don't really have enough to sketch the line. So this is not enough information. So not enough info to graph the line. You need one more point. So what you can do here is, you can solve the equation for y if you want to do that, and then find a point, or you can find a point in the form that it is. I would probably just solve it for y real quick. Takes 2x minus 3y equals 0. Get the y by itself. Divide by negative 3 here. And you get y equals 2/3 x. And then just pick an x value here. I'm going to pick an x value that will give me quote-unquote nice y value back. I'm going to pick x equals 3. So if I pick x equals 3, all right, watch what happens here. You get y equals 2/3 times 3. 3's cancel, and you end up with y equals 2. 3's divide out there. And so you get a quote-unquote nice value there for the y value. And you can always do that. If you solve the equation for y, you'll always be able to find an x value that will give you a quote-unquote nice y value back, and you can avoid using fractions. Now I have enough information to sketch the graph, right? You have 0, 0, and then you have 3, 2, and there's my graph right there. All right, and so there's my equation. There's 2x minus 3y equals 0. All right, and so if I'm continuing to graph using intercepts, if I'm graphing x equals 3, well, wait a minute. That one I know the graph is vertical, right, because of the way the equation's written. And so when you can see that you've got a vertical line or a horizontal line, graph using the intercept, that's fine, but you don't have to do a lot of work here. You know that this is a vertical line that passes through the point 3, 0. There's my x-intercept. And notice there is no y-intercept for this equation. Right? There's no y-intercept because it's a vertical line. Right? And so in the same way, if you get y equals, let's say, -1, right? Because it's y equals a constant, we recognize that this is a horizontal line. And so because I know it's a horizontal line, I can use the y-intercept here, but there's not going to be an x-intercept, is there? Because of the fact that this is horizontal, it's going to be parallel to the x-axis. And so you just draw a horizontal line through this point 0, -1 right here. And here's my horizontal line. Right? And so there's no x-intercept on this line. All right, so we're doing really well as we're going through all this information. And so I think the last thing I want to talk about here for a few minutes, so we've talked a lot about graphing lines. And so for a few minutes, I want to introduce the idea of the slope of a line, and then we're going to be done for the day. And so the slope of a line is, first of all, a measure of how steep the line is and which way it slants. Right, so a line that, and the letter that we use for slope, by the way, is the letter M. So M is going to be equal to the slope for a line. Right, so a line, when I say the direction that the line slants, right, the line could slant upwards as we go from left to right. Right, so a line that slants up as we go from left to right, the slope is positive. So M is positive here. And for a line that slants downward as you go from left to right, so let's see. So we have a line that looks like this one. Right, this one slants down as you go from left to right. So this is, and so here the slope is negative, and M is less than 0, and so slope is negative right here. And sometimes you'll see this referred to as a falling line as you're going from left to right. And the other line, the first one I sketched, this is a rising line, like so. All right, so that's one thing for sure you need to know about a line, is that the sign of the slope describes which way the line slants. All right, and so then let's actually talk about the steepness of the line, how steep it is. So now we're talking about the numerical value of the line. The slope is defined in words to look like this. So let's say we have a line that passes through, 2 points like this. Like so. Then when you're talking about 2 points on a line, you can identify the quantities as you go from one point to the next, what we call the rise as you go from one point to the next. This is the rise right here. And then the run, and let's put that in a different color actually. And then the run is this distance right here. As you go from one point to the next, that's the rise and the run. And the slope of a line is simply defined to be the rise divided by the run. And, you know, if you have a graph where you can identify this by pictures, you can actually count and see what the rise and the run is. So like on the graph that I just sketched, right, the rise is 1, 2, 3, 4 is 4. And the run happens to also be 4 on this problem. So the slope on this particular line that I sketched right here is going to be rise divided by run, or 1. This line actually has a slope of 1. And that's just kind of coincidental that I drew a line where the rise and the run would happen to be the same number. But so this is important right here, that the slope in words is defined to be rise over run. Now, if we look at that picture, or in just a picture in general, if you are talking about, it would be nice to not have to always count on a graph to calculate the rise and the run, and we don't have to do that. So if we have 2 points in a line, and let's say that this one is x1, y1, and this point right here is x2, y2. Those are subscripts on those points, and that those subscripts are simply ways of distinguishing those 2 points from each other. Then the rise on my graph right here is this distance. There's the rise right there. And then the run is this distance right here. And we can actually calculate that. The rise is simply, if you just take the 2 y values and subtract them, you get the rise. And so the rise is simply y2 minus y1. Right? And then the run is simply, you know, you're moving horizontally there. That's the difference in the x coordinates. And so that's x2 minus x1. And so another way of writing out the slope then, so you have slope equals m equals rise over run, but it's also equal to, as a calculation, y2 minus y1 divided by x2 minus x1. So that's nice to know that that's a way of calculating the slope. See, so you don't even need the graph to calculate the slope. So what is the slope of the line passing through -1, 8 and 4, 7? All right, so what you simply do, and it doesn't matter which one, but you simply call one of the points x1, y1, and one of them x2, y2. And the nice thing is it doesn't matter which one is which. If you subtract in the opposite order for someone else, that's okay. You'll just get the signs to be opposites as far as numerator and denominator, but that won't change what line you get. And so the slope of this line then would be y2 minus y1 over x2 minus x1. And so it'd be 7 minus 8 over 4 minus -1. And so that would give you -1 in the numerator and 5 in the denominator. And so that's -1 over 5. So the rise is -1 and the run is 5. Right, and so that's the slope of the line is -1/5. Now someone else could have subtracted in the opposite order on this problem. They're still going to get the same line. I'm going to show you that. So if you do the opposite order here, you get the slope to be 8 minus 7 over -1 minus 4, and this person gets 1 over -5. Well, those are the same thing. The rise, in that they're the same thing in that you get the same line either way. Now the rise is +1 and the run is -5. I'll show you that on the next screen, and then that's going to be it for the day. So if you have a line that passes through, let's say 2, 1, and has a slope of -2/3, I want to graph the line. Well, that slope of negative 2/3, first of all, because the negative sign on in the front of that fraction doesn't mean it's a negative on both the numerator and the denominator. That's two negative signs. That's a negative sign on the fraction, and so that means it's either on the numerator or it's on the denominator. It's not on both of them. But it doesn't matter if you graph this out, you're going to get the same line. You're just going to get different points is all, but it's the same line either way. So you know that this line passes through the point 2, 1. So here's 2, 1 right here. And if we use negative 2/3 as the rise and the run, right, if we use negative 2/3, then the rise is negative 2, so it means we go down. And then the run is positive 3, means we go to the right. And we get that point right there. But someone else might have done this differently. Someone else might have said that the rise is positive 2, so we go up 2. So there's where the rise is positive 2. And then the run is negative 3, which means we go to the left 3. But notice a person who did that is getting the same line. Right? Those points are on the same line. It's just that you get the points in different directions from the starting point there. And so it doesn't matter which one you use. You get the same line either way. Right? All right, so we have definitely done a good job. We've gone through all this the introductory stuff on graphing lines. We started talking about slope. And so more, what I would say here is more on slopes and equations of lines next time. On Tuesday of next week. All right, so be working on homework. Remember, you have WebAssign homework on quadratic equations that's due. So WebAssign 10-1, 10-2, 10-3, 10-4 is due on April 3rd. So be working on that and get that done. Don't hesitate to try to get in touch with me if you have any questions.